So we have Avi Mendelson from Microsoft, Scott Shenker from Berkeley, whom you have already seen, Radu Sion from Stony Brook, Skuler from Alcatel Lucent, and Eyal Waldman from Mellanox, whom you already saw. And the question I have asked everybody is, in your perspective, what are the most important challenges in cloud computing? And for each such a challenge, how do we solve it? Do we have to go outside of the box, or this is just another copy of what we have seen before? And when we look at clouds and the challenges in cloud, you can't see it, but each one of the people like me, I would see, you know, a different issue, and each one of the speakers here probably see a different picture from the cloud, right? And the pictures and the meanings have nothing to do with the person. I have just picked them up and don't even try to figure out what they mean. But what I want to say is that when you see a cloud from different angles, you see different stuff. And we will hear, you know, in a few seconds about what are the challenges that each one of the speakers here have in mind. And then, you know, how do you solve those or address those challenges? Do you go out of the box, or this is just just another copy of IPv6, whatever we saw before. So with that, let's start with our presentation of the speakers, and it will be by alphabetical orders. So Avi will be the first one. I will shortly introduce the people who haven't been introduced today, but I will do it very shortly, and I apologize. So Avi Mendelson manages the academic outreach program at Microsoft R&D Center here in Israel, and he's also a visiting professor at the TCE. Before joining Microsoft, he was, maybe some of you know that, he was a senior architecture at Intel Israel, where he led the CMP architecture for a CodeDuo family of processors. What you probably don't know, that next year he will be served as a general chair of ISCA, which is a computer architecture conference, which will take place next June here in Israel. Avi.
Okay. So, actually there are many different challenges, and I'll try to address only a few of them. And I think that I'll try to cover a few main things that at least I think that I'm not sure that this is the main challenges of the cloud, but I'm sure that these challenges are much different when we talk about the cloud and when we talk about regular computation, or what we use to think about a regular computation. And again, it is data driven, it comes with a business model, opened up for new types of operation, and some aspect about the research, and I'll try to do it very short. Okay, data driven. So actually everybody knows, or at least we think, that Moore's law was broken only due to the power and the thermal walls. Actually there was another factor that I rarely hear about it, and another factor is that actually for a long time we didn't found any good reason to produce better computers, because we failed to find a market for it, and we didn't find any killer apps. So we could actually produce better computers, but nobody really needs them. So I think that part of the revolution, or part of the different thing that the cloud brings, is the fact that data is growing exponentially, and actually the computation power that we need in order to support it, compute it, and so on, this becomes the new Moore's law these days, which is more about data and not only about computation that we used to think about it in the past. And I think that this is a kind of out-of-the-box thinking about the computational problem. The other aspect is that the cloud, unlike grid, comes with a business model, which means that a company wants to earn money out of it, and Eventually, sooner or later, it will become a commodity, which means that it is not clear how many of the companies that are served right now as cloud providers will continue to survive or will survive in the future. There is a big question because the margins most likely will be will shrink. The risk that the companies are taking is quite large, and it is clear to me that very few of the companies will survive. But also the good part is that it drives a lot of innovation because people start to understand that some small changes may make a big differences. Which bring the issue that small startups and small and smart startups can successful to compete with large companies, and this is, I think, very important for the community. By the way, it may risk large companies like Microsoft, IBM, and so on, but it is a trend that we start seeing in many different aspects. That the market goes to special computing and the market start to favor small companies and not only the large companies. And if you can't beat them, join them. The fact is that most of the big companies start to actually support startups, and a good example is the both Google and Microsoft in Israel just opened or announced that they are going to open accelerator centers, which are actually aimed to support startups and to work with startups, and they start to begin that they need to leverage innovation that comes from startups and not only to build things by the big companies. Again, this is a totally different aspect of the business that we are doing. And I want to conclude about some impact on education. Apparently, all the issues that we are moving to big data or to handle a lot of data means that many things need to be changed dramatically. It means that even the way that we used to teach in the past, parallel computing, it's not clear that it is valid anymore. Right now we are talking about MapReduce, Hadoop, Dryad, and other programming environments which are quite different from OpenMP, for example, or other languages and other methodologies that we used to teach. It doesn't make sense to have hundreds or thousands of computers and using shared memory. Most likely we need to move to something like message passing, or maybe a different method, or maybe some a hybrid, but we need to change the way that we think about programming languages and programming environment. Something else that statistics become extremely important. You cannot handle any bit and byte of data that you receive. You need, by using statistic methods, you need to understand what you like, what you're looking for. You need to understand how to compute things and so on, so that the deterministic way of thinking most likely will change, and again, data analysis must become part of any CS and EE education colloquium. I believe that this is also something that we need to change in the short term. It goes back to statistics, machine learning, and so on, but again, we need to emphasize much more on data movement, data manipulation, and not only about the algorithms that do the computation and itself, but the data is much more important than we thought before.
So our next speaker is Scott Shenker, and you should know the alphabet order. And since he introduced himself so well, like 2 hours ago, I have nothing to say. Scott. Okay.
So I want to talk about programming in the cloud. This is joint work with Matej Zaharia, Jan Stojka, and Ali Gotzi, who are colleagues of mine at Berkeley. So I want to start with a riddle. Why is the cloud like the internet? So the answer, or one answer, is they both represent the triumph of statistical multiplexing. What made the internet great was the fact that when you schedule individual packets, packet switching is more efficient because you can provision for the sum of the averages, not the sum of the peak rates. That's what made the internet work. So what about the cloud? The cloud is all about sharing massive data centers. So rather than everybody buying their own individual cluster, you go and you use these large shared data centers, and I think I'm about to be reprimanded for walking away from the mic. Okay, so the cloud, it's the same thing. We share huge data centers, and we ride statistical multiplexing. So the implications of this are that there is a new unit of computation, and that is these warehouse-scale computers, these computers that are 100,000 machines. But that's the unit of computation. When you run a job in the cloud, that's what it's running on. That's the computer we use now. So there are two fundamental challenges. Now that this is the new computer, what's the operating system? And what's the programming paradigm? Okay, so I'm going to go very quickly through the operating system. The operating system, the basic functionalities, you need to make these 100,000 machines look like one. So there are lots of low-level things like file systems and so forth, and that's been solved by a lot of people. Pretty standard. But there's one question that people are still struggling with is, how do you share this? You're basically having many jobs running concurrently on this cloud. How do you share it? How do you share it fairly? And it turns out that different jobs have very different requirements. Some need lots of cores but don't need much disk. Others need a lot of network but they don't need a lot of cores, and so on and so forth. So what does sharing mean here? What does fairness mean here? And many people said, well, fairness, it's in the eye of the beholder. How can you possibly decide that? Turns out there's one answer. One answer. That is dominant resource fairness. If you insist that your sharing mechanism is strategy proof, and that if you end people sharing it, you each get at least 1/nth of the goods, there's one answer. And for the game theorists in the audience, and my guess is there are more than I would have guessed, this is Kalai-Smorodinsky bargaining solution. It turns out with Leontief profiles, it's strategy proof. If you understand what that means, great, raise your hand. Otherwise, ignore it. You'll never need to know it. But it does mean there is one method. But I want to talk about the programming paradigm because that's actually a little deeper question. So what's the hard problem of programming this cluster of 100,000 machines? And it's obviously the large-scale parallelism. No, that's not the problem. As was mentioned earlier, so we have these huge data parallel algorithms. They're embarrassingly parallel. So either we have applications that aren't parallel at all, and if there's no solution, there's no problem. It's not going to run using lots of machines. Or it's embarrassingly parallel. We can use as many machines as we want, and making it parallel is not the problem. That's a solved problem. What is the problem? The problem is failures. When you scale up a machine, there will always be some machine, some individual CPU that's down, or some disk that's down, or some machine that's running slowly, a straggler. So when we run our PC and the disk fails, we assume the machine's dead. When the CPU dies, we assume the machine's dead. When you've got 100,000 of them, there's always going to be some failure. So you've got to learn how to operate with these partial failures. And so when I say failure here, I mean either fail, stop, or just operating very slowly, and the straggler phenomenon is actually the dominant phenomenon by a very large measure. So how do you cope with these failures? There are three strategies. One is your application just doesn't care. You're computing the average of some metric. One of your machines goes down, takes the disk with it. You lose that piece of data, but you've got 99,000 other samples. Who cares? But that's not a general solution. It's true for some applications, but it's not a general solution. Then there's checkpointing, that you run the application, and every so often you checkpoint it, and then if one of the machines that it's running on fails, you roll back to the last checkpoint and you restart it again. Checkpointing is pretty heavyweight. Restarting the whole thing is pretty heavyweight. Not a great solution. Or you can do deterministic partial re-execution, which means you look at the machine that failed and you just rerun what it was doing. Okay? So that's the clear winner. That clearly, it's much lighter weight. You're not doing global checkpointing. It's much finer grained recovery. You're only recovering what failed. And you can even do it preemptively. If there's a part of the computation you really don't want to take long, you run it twice in 2 different places at the same time. If one goes down, you don't even notice it. This has been implemented by several proposals. At Berkeley, we work on something called Spark, but similar things are in Dryad and other places. So this isn't particular to Berkeley. This is a sort of what you have to do on the cloud. But it does require support from your programming framework, your programming paradigm. You've got to eliminate non-determinism. So if you were going to run something on this machine and it turns out that's running slowly, you want to rerun it over here, you got to get the same answer. Immutable variables are your recovery unit. You checkpoint them to disk. You're not checkpointing the whole machine, you're just checkpointing individual variables. They're all immutable. And the way you name them is with lineage. So if I took a checkpointed variable x and I did operation 1 and then operation 2 and then operation 3, what is its name? It is operation 3 applied to operation 2 applied to operation 1 applied to x. Why? If I can name it, I can recreate it. Because x is in stable storage, and if I know the name, I can reproduce it. So you don't have to worry about checkpointing on a global basis, because anytime you put something in stable storage, you then just create its ancestry of how to recreate it. Now, this applies only to contexts where you have these huge sort of granular updates. I mean, there's highly parallel updates. You don't do this if you're computing pi to 100,000 decimal places, because the name of that variable gets to be as long as the program itself. But here, most of these highly data-driven applications are highly parallel, and you only have a few map applications, a few reduced tasks, and you can name it. So just to end, so in answer to the opening riddle, why is the cloud like the internet? There actually is another way, and that is that scaling is all about how you handle failures. The way the internet scaled is the unit of failure was a packet. It was individually recoverable that could be recovered by the ends in the network. You didn't have to build it into the network. The network just dropped a packet and it gave up. The ends recovered it. And all we're saying is to make the cloud be able to scale, you make variables, individual immutable variables, be the unit of recovery. That's what you recover. You don't do global checkpoints. So, there's a debate between the database community and the sort of large data center community about MapReduce versus standard database technology. And Mike Stonebreaker in particular has written articles sort of complaining that, sort of MapReduce sucks, and, why don't you use database technology? And he's absolutely right. When you look at it from a query processing point of view, MapReduce is terrible. I mean, it's like elementary school. But it understands failures, and databases never have, not at this way. So this is why MapReduce and things like Dryad and so forth that have come after it, that's why they won the battle. They understood how to handle failures to scale. And that's going to be the key to growing the cloud. So I just want to end with this observation that we tend to dismiss the internet as just a network. It isn't just a network. It is the biggest, most scalable software system we have. And so when we're looking for lessons about how to build big, scalable software systems, this is where we should look first. Thank you.
So our next speaker is Radu Sion. He's an associate professor for computer science at Stony Brook University. He likes to build systems, and he did not want a very long introduction. So I won't do it. Cool.
All right. So thanks for having me. It's great to be here. This was great so far. I don't know how I can top Scott's talk, so I'm just gonna, this is gonna be bullshit, okay? So I apologize in advance. All right, so I'm here for various reasons. I do cybersecurity mainly, but I also run a cloud startup, and I do all kinds of stuff with clouds. And what I'm gonna do now is I'm just gonna throw a bunch of things at you, and that's the end of it. And then I'm gonna, hopefully we'll have a discussion. Here's what I'm gonna throw at you. What is fun, or at least important in the cloud? Well, here's a bunch of things, okay? And that's the end of my talk. Security, risk insurance markets, programming the cloud, interoperability and standards, appropriate pricing paradigms, and about 1 billion other things, okay? What is the cloud? We don't know what the cloud is, a big buzzword. We don't have time to go through this. At Systor, I had about an hour to talk about what this cloud is, and we had a little bit of fun. cloud is a big buzzword, okay? It depends on what layer you look at. Are we looking at infrastructure? Are we looking at, are we outsourcing virtual machines? Are we outsourcing services? Are we doing application level stuff? It's so much of a buzzword. It's very difficult to talk about cloud in 10 minutes and identify that one issue that works. So that's why I'm just throwing these things. But these are cool things that kind of penetrate all these layers. So security is important, and it's kind of my little thing that I'm doing. So I'm not going to talk about security too much. I'm going to talk about these other things that I don't know anything about. So risk insurance markets, programming the cloud, and again, you know, great minds think alike, may I say that? So I'm not going to talk about programming the cloud, I guess, anymore. Interoperability and standards and appropriate pricing paradigms. And so here's a bunch of numbers. How much does a CPU cycle, I promise Ramsey, I'm not going to mention picocents, but I am mentioning picocents. How much does it cost you to do 1 unit of compute at home, and how much does it cost you in the cloud? What is a unit of compute? I have no clue. I'm calling it the CPU cycle. I'm normalizing to x86, 2 gigahertz EC2 core, single core. How much does it cost you to do it in the cloud? It costs you about half a picocent. What is a picocent? It's 10 to the minus 14 US dollars. That's what a picocent is. How much does it cost you to run that at home or in a small business? About 30 picocents. All right, so here's the number. This is one data point, okay, the picocent. Here's what the providers charge you today. You have Google, you have Rackspace, you have Amazon, Microsoft. This was circa 2008, 2009, but many of these numbers hold, and Rackspace is basically virtually the same. Here's another cool, interesting thing. At scale, you know, when I was in high school, they were telling me, oh, okay, well, in computing, what counts is service. And I'm old. I'm really old. So in my old days, my young days, they told me that computing, the whole thing in computing is service. That's what takes a lot of money and resources. Well, the breakdown of CPU cycle, if you see at scale, what counts and the opportunity for research and all kinds of cool things is energy and hardware. Service is almost inexistent. Why? Because we've become very efficient at managing stuff. Now, let me step back a little bit and mention what I exactly referred to here. Because I'm not referring to applications or anything like that. I'm referring to outsourcing of virtual machines. And again, the 10 minutes hit me in the head because if I were to have more time, I would be able to explain this in much more depth. But again, when you're talking about outsourcing CPU cycles, we're talking about CPU cycles and running one cycle. Forget about applications, forget about all kinds of cool things on top of that. One cycle, the breakdown of a cycle is energy 30%, server 50+%, server hardware. Here's another data point. How much does networking cost? It costs you 5,000 picocents, or 3,000 plus picocents per bit to transfer networking. So me as a small to medium-sized business can buy networking at thousands of picocents per bit. As a large business, I can buy upwards of 2,000 picocents per bit. How much does Amazon actually? That's a data point I know. How much does Amazon pay for a bit? 400 picocents. So what very few people understand, and this is kind of a summary of my 4-hour-long talk that became a 1-hour-long talk in Systor, and this is, this is going to be a 2 minutes long talk. The reason we love the cloud, at least in terms of infrastructure, is because it acts like a glorified CDN. Because your application that lives in the cloud, all the incoming traffic to that app will cost you only 400 picocents or 530, something like that in Amazon today, whereas if you were to host it at home, it will cost you thousands of picocents. So the reason you go to the cloud, at least at infrastructure level, is because you're saving in networking. The cloud is a CDN for your app. There's no other reason. You're not saving in compute cycles. In fact, if you have an application that you're the sole client of, it's not worth to go to the cloud. That's as much I want to tell you about that. How much does storage cost? Well, here's another nice story. Well, it costs about 100 picocents per bit per year to store 1 bit and keep it alive. Alive means within less than a second latency. How much of that is energy? Well, in this particular slide, if you amortize over MTBF, is a majority. It dominates. It's roughly 3 times the amortized acquisition cost. However, if you take Bianca Schroeder's story that says, hey, disks die much faster. In fact, if you go beyond that and say disk will be replaced in 3 years, if you amortize to 3 years, then amortized acquisition becomes 350 picocents, but still within the same ballpark as energy. What does this tell us? Well, it tells us a million things. I don't have time to tell you a million things, but one thing I can tell you is that Google, who by definition pays a little bit more than energy than we as retail, will not have a significant opportunity to give us much cheaper storage. Even, forget about data replication, all these other cool things. Storage will not be much cheaper in the cloud, ever, for many reasons. And there will be other advantages why you may want to pay more for storage in the cloud, but cost will not be one of them. Now, here's another story. Now, everybody goes to the cloud. And the question is, well, why do we go to the cloud? Because when you outsource to the cloud, here's what happens. it seems amazingly expensive. Computing in the cloud at 8 cents an hour, over 3 years you pay about $2,100 to keep the smallest instance, actually not the smallest, but the small instance is Amazon. And then the utilization for that instance is going to be still low because you usually take a traditional application, you can outsource to Amazon, and then you wonder, hey, my costs are going to be $2,100 a year. And then if you were to buy a machine, if you were to compute stuff at home, and again, this is a hypothetical irrelevant scenario here, right? Because we're not talking about home users here. We want to talk about businesses. But I'm just showing you a little bit of a type of discussions I'm having with people on Wall Street that basically tries to evaluate why they may want to go to the cloud. If you compute at home, it costs you $400 for energy over 3 years, and acquisition about $500, the equivalent of the small instance. So it seems like it's not worth to go to the cloud. And then networking, by the way, costs you, in the cloud, Amazon charges you $582 if you transfer over 300 terabytes. So here's another data point. I know I have about 3 more minutes. I hate people who take much longer than their slot, so I'm going to shut up in 3 minutes. I promise you that. Now here's something cool that some people have done. They looked at temperature of CPUs in the cloud, and they tried to estimate utilization of the cloud CPUs. And it turns out that, common wisdom is, hey, these clouds are so cool and they can go to 60, 70% utilization. That's why they can offer you cheap CPU cycles. Well, it turns out that's not true, right? If you look at this kind of temperature-based estimation, which was validated in the real data center, what you get is, 15, 20, 30% max. The highest level utilization was on a Monday between, 3 p.m. and, I can't read those numbers anymore, but somewhere midday, and is less than 35% in the cloud. This is a cloud server, the actual hardware. You could read the temperature off the hardware. So this kind of confused me. So this is another data point I threw at you. All right, here we go. So here's one cool thing. We need appropriate pricing. Right now, the problem we had before was we bought this instance, and we used it at 12%, but we paid at 100%. We paid for per hour. And that's not something that will hold in the longer term. I don't want to go to the cloud if that happens. I want to pay for the cycles I'm actually using, not for the time I'm resident. I want to pay for the amount of cycles I get. So it would be cool if I could pay per cycles. And of course, great minds think alike. So Dan and Orna from Technion have a very similar project going on now. So great minds think alike. And then CPU cycle markets. This is another cool thing that I'm seeing coming. I'm seeing Wall Street getting into the business of selling and trading CPU cycles. That's not going to happen today or in 5 years. It's going to happen in about 10 years, maybe 15. But it's going to happen. And for that to happen, we need standards. We need things to be compatible. We want rack space cycles to be equivalent or somehow convertible into Amazon cycles on demand. So we need standards. Okay, I'll take 1 minute bonus, okay? Security, we have security. This is my main thing. This is what I do, okay, security. And frankly, here's the deal. The usual suspects, there's nothing new in the cloud, okay? All this stuff has been done. We've been doing this for tens of years. You have network security. You're going to relabel everything you do clouds because it sounds cool. You're going to get more funding or whatever everybody wants. But most of this stuff is the same. And then you have all this virtualization, isolation, all this stuff that people have been doing. And all of this stuff, again, there's not much stuff new. But here's what happens new. Here's the new story. The new story is that I don't trust the cloud. I want all kinds of guarantees from this remote entity that I have a $25 a month relationship with, and I want these guarantees, and these guarantees should be much stronger than $25 that I pay. And here's what I want. I want data integrity, I want query correctness, I want confidentiality, query privacy, access privacy, all these cool things I need and I want, and I have no clue how to do them. And Diffie, who, by the way, some people here know has a very good opinion about my physical appearance, and I'm not going to get into details, but ask the people that run the SIS store. Diffie had this story, okay? He says, hey, listen, we have all this crypto we've been doing today, and I 100%, we've been saying this for years, and again, I'm very much behind this. So we have all this crypto, and we're trying to secure the cloud with all this crypto. And it's not going to happen anytime soon. We're not going to be able to do stuff under the envelope. We're not going to be able to achieve confidentiality. We'll be able to get integrity. We'll be able to get a few other interesting things. We're never going to be able, in the foreseeable future on Turing machines, unless we rediscover new trapdoors, we won't be able to get full computing under the envelope. So the question is, can we do something cooler than that? And so again, take something home with you. security, risk insurance markets, programming in the cloud, interoperability, appropriate pricing paradigms, and so on. And regarding programming in the clouds, I've been hearing a lot of discussion about MapReduce and trivially, embarrassingly parallelizable things. I believe the interesting part about programming in the cloud will not come for scientific apps. We've had the grids and all that stuff doing that for 20 years, 15 years or so. I think the cool thing in the cloud will be when grandmother will be able to plug and play a bunch of things together, push a button and deploy in the cloud within 20, 30 minutes. And there's a million startups that try to do that today. And we don't really know how to do it. But I think that's the cool thing that will drive the killer app for this cloud becoming more than what we have today. And of course, also getting Wall Street in the cloud, but that has to do with security and all that. And we'll talk more, I guess, during the panel. And I'll shut up. Oh, one more thing. If you come to New York, we go sailing. So this is a catamaran. The guys in Sistor already know this. This is my old trick. But I'm showing you me and the friend on the cat. So I need always a partner to go sailing because I'm not heavy enough. And then when this thing goes in the water, it dips completely down. So you have to dive and get it up. It's very difficult. So you want enough weight to keep it back up from diving. So it was fun talking, and I hope you'll ask a bunch of questions.
Was not introduced today, but still I'll keep the introduction short, and I apologize for Dor. So this is Dor Skuler. He's very capable of talking about the cloud because he's heading the cloud business unit in Alcatel Lucent, and he will talk about what he sees in the cloud. Thank you, Dor.
Okay. So, is cloud about TCO? I'm not sure. I'm not sure the driver and why cloud is cool and why people are moving to the cloud is about higher utilization of CPU. From all the people we talk about, it's about simplicity. It's about the fact that as an app developer, you don't need to care about the underlying infrastructure, right? If in the past you built an app, you first had to buy some servers and get a network installed and do all the IT stuff and then do what you actually raise money to do, right? Build a great social media app or do whatever. The real reason that people move to the cloud, the real reason it's a revolution, is, at least in our view, is simplicity. You don't need to worry about capacity planning. You don't need to care about infrastructure. You don't need to care about all of the complexities that are just a given for you to be able to innovate. But it's still lacking. And the two aspects that I'm going to talk about, the two problems, which I think, to your question, Danny, revolution or evolution, I think a revolution is needed, are the two things I'm going to talk about. The first is, Alcatel Lucent, what am I even doing here on stage? We sell stuff to phone companies, right? So let's look at how phone companies are running. In phone companies, right, the telcos, the AT&Ts, the Bezecs, whatever, the way you deliver any service, your phone service, a video service, SMS messaging, any service, you first have capacity managers that say, hey, what's going to be peak for SMS messaging in New Year's Eve in 2014, right? Why do you need to guess so far? Because it takes them 2 years to build out anything, right? And they build it up for peak, 10 million SMS messages on dedicated hardware. By the way, servers in the telecom industry, we call it ATCA, live how long? 2 years, 3 years? 15 years. We build servers that live 15 years, right? Right along Moore's Law. So what we do in the telecom industry is we build dedicated equipment. For each one of those services, we build an entire stack just for that service based on capacity planning. Because it's telco grade, we do it N plus N. So we build another parallel stack just in case for the full capacity. It runs at 15% utilization if you're lucky. Because guess what? It's not New Year's Eve every night, right? Or Mother's Day every night or whatever you peaked for. And because it takes you 2 years to deliver it, then you're way behind the innovation cycle, right? So by the time some cool startup creates a new video conferencing application, let's say you started at the same day, it will take you 2 years and a bunch of capital to be able to do the same thing at the same time. That's a problem we have in the telco industry internally. The reason it matters is that the network connects the cloud. When you look at capacity projections, it's going to grow 30x in the next 5 years, right? So we have to find a way to grow the network much faster. We have to find a way for the network to innovate much faster. And doing it the old-fashioned way of piling boxes on top of each other with complex capacity planning, with end-to-end redundancy, doesn't work. So problem number one, how do you leverage cloud technology to build networks? Okay, to build the network itself. And that's something we're working on a lot. Problem number two, is the public cloud good enough? Well, we didn't know. So we just asked, right? We did the world's most comprehensive survey. We published it last Thursday, so you're welcome to go to alcatellucent.com and look at it. But we have 3,500 enterprises that actually use Amazon. Okay? They're not shadow IT, but they actually use it. And we asked them, well, why do you also have a private cloud? Why don't you just go to Amazon? And I was sure the answer is going to be security, security, security. We don't trust it. It's different. No, performance is the number one issue. Performance. They want guaranteed latency. They want guaranteed bandwidth between the back end and the front end. They want guaranteed SLAs, guaranteed quality of service. They want VPN. And also, ease of use. In some places, ease of use is more important than security. Meaning I want a lot more, but I want it to be super, super simple. Super, super simple. So how do you do that? How do you solve both of those problems? We believe it's around SLAs. It's around creating a cloud that's a lot more tuned to performance. And you need to do that in a radically different way. So there are a few things we think that need to be different. First, the network itself. The network, definitely agree with Scott, the network needs to be abstracted. It needs to be abstracted, but not just inside the data center and not just load balancers, but the network. For us, the network is with a capital T. It's the WAN, right? It's what you get from your wireline provider. It's being able to get complete end-to-end networking services all the way to the end user in a programmable way. One. Two, and here I disagree with some of the previous things that were said, it's not about building mega data centers. They're needed for certain type of applications, but it's actually about building lots of little clouds very close to the end users, pushing them all the way out to the end users. Actually, it's not that surprising. CDN works the same way. Akamai works the same way. Instead of sending, every time you want to see a YouTube clip, right? Instead of going all the way to Google, downloading it and pushing it all the way back for individual users, the CDN caches it locally, at your local exchange, at your local CO. Or an Akamai CO, and then there are peering agreements between the two, but it doesn't matter. It's close to the end user. Okay? We believe that to get latency down, to get bandwidth costs down, and bandwidth costs are very expensive right now, and they're one of the reasons that also network capacity is going to go through the roof. It doesn't make sense to send everything to, I guess the closest Amazon site is Ireland here, and back. It would make sense to have a cloud in Haifa. Maybe not a huge cloud, but a cloud in Haifa, and another one in Tel Aviv, and another one in Eilat, right? And when you look at the US, a lot more, okay? A lot more. So those are the two fundamental things that we think need to shift. The cloud needs to be distributed and somehow managed together as though it's logically just one cloud, but a cloud that's smart enough that it knows the SLA of the application and decides where to place each virtual machine, each workload. Should it be in Haifa? Maybe the front end should be in Haifa and the database should be in Ireland, or replicated in Ireland and a central one in Tel Aviv. Who knows? Each app is different. You need to abstract the network. You need to manage all of those things together. And also federation is important. So there's a hidden assumption in cloud. Infinite resources, right? Otherwise it doesn't work. But when you talk about individual carriers building clouds or smaller companies building clouds, they're not going to have infinite resources. So they need an easy way to use someone else's resources. So that's federation. And one of the things we're doing is allowing from the same interface, you go and you ask a cloud for stuff. If it doesn't have the resources, it will go get it from another cloud. So at a very high level, just to give you a snippet of what we're working on, we believe that a few things are going to happen. And this is specifically to the service provider network or the service provider companies, right? They're going to build out clouds. Those clouds are going to be distributed. They're going to be managed holistically as one entity. Inside of them, it's going to be multi-vendor. Some will like OpenStack, some will like CloudStack, some will still like VMware. Maybe tomorrow there'll be something else. You know, who knows? It will be all kinds of hodgepodge. but you need to be able to manage this in a multi-vendor way. You need to burst onto Amazon if you need to do that. You need to be able to programmatically set bandwidth, latency. All of those things need to happen. And the workloads that will work on top of those are both telco services. So the 4G network, and there are some carriers today that are building their 4G network on top of the cloud. No boxes. They'll have an antenna, optics to their regional clouds, and apps. A radio controller, those of you that come from the field, think of RNCs, MMEs, all these fancy carrier-grade to the nth degree applications are going to be apps on top of the cloud. And of course, cloud services for the wider industry, if you need high performance, if you need low latency, that will all be optimized through this type of an architecture. So that's pretty much kind of our view of the world. We think it's a bit different. We're happy to say that we're developing most of this in Israel. And there are also a lot of algorithms, a lot of optimization algorithms, a lot of stuff that I know Danny and his team are working on. We still have a pretty deep research team in Bell Labs. We're publishing a lot of papers on these issues, and we really, really welcome the cooperation of academia to help us out. That's it.
So our last speaker is Eyal Waldman, who is the CTO and president of Mellanox, and he will definitely have a different view, maybe.
I actually agree with everyone, so.
He tries to sell.
That's true. We sell to everyone. So we actually don't really care if it's small clouds, large clouds, where's the storage, where's that, we can sell, we can improve everything you do. And we're not just saying this. So we talked about this. Again, the evolution of going from mainframe, client, server, cloud. I'll try to be short. We've seen this multiple times. So basically, if you think what you want to do, regardless if it's small, large, how much it costs, you want to connect the CPU. And this is kind of, if you think, it's the deaggregation of the basic building block of a cloud. You have a bunch of CPUs. You have memory, you have storage, and then you have applications, and you want to connect all of them together. So basically what happens is the network is becoming the main kind of differentiation that you can have in connecting those resources together, and that's exactly what we do. So I won't go into all of this, but basically there's a lot of data that you want to analyze. There's access to mobile devices. There's a lot of issues you want to go into with the new challenges we have. Everybody talked about data security. I won't repeat this. And again, the interconnect is the cloud. So basically, you have those basic elements from x86 from Intel. You have the flash or the DRAM. You have the disks, and then you want to connect everything. And basically, what you want is flexibility, low latency, high bandwidth, and very resilient infrastructure. We talked about this trend, and I won't repeat this, but basically, the performance of the CPU need to be matched by the performance of the network, and we've done this in multiple ways. We talked about our products, and basically, you want to have the most efficient network in order to run all of the different type of services the network wants to provide you. So with the elements that we have, what's important is the bandwidth, latency, remote direct memory access, the power, density, consolidation, management, partitioning, virtualization, and cost. And if you think of how you connect that, that's one of the strategic advantages we can give you. With that, thank you.
Okay, so now we're to the more interesting part where you ask questions and the panelists answer. But first, if anybody of the panelists would like to argue against or for some of the other presentations or say something related to stuff that somebody else had said.
I'm heavy enough for the catamaran, so.
Okay, so it's up to you guys to ask very good, strong questions. And we have a mic here, so whoever wants to be the first.
I have a question for you guys. How many people here use Amazon? Can you keep the hands up? Amazon EC2, let's put it that way. How many people use Amazon EC2? Why?
Yes, so I'm waiting.
I don't believe in the edge servers. I have a little, I'm trying to understand how the economies of scale would work on these very small edged data. So I'm imagining you're suggesting they will be small.
Yeah, I mean, look, I think like everything, kind of like a CDN, you're going to have tiers, right? Sometimes it makes sense to be in a mega huge data center, and sometimes it makes sense to be pushed all the way to the edge. But the economics are actually very interesting when you look at total cost of everything, including backhauling, right? Cost for the end users, and the amount of automation that's needed. And one of the lecturers spoke about that. I think it was also used on about the amount of engineers that you need in order to manage servers. And I think that's, when you look at the economics, that's where it's at. If you can build a totally autonomous cloud that sits in the edge, it doesn't need an IT guy. It comes up automatically. It self-heals itself if it's broken. It self-backs itself up, et cetera, up to a point, you know, when servers die, you decommission them, and when 50% of the rack that you threw in a CO in a central office, which is what you probably have in Haifa, dies, you forklift it out and you put a new one in, and it's operational again, right? If you get to that level of autonomy, then the real costs of ownership as far as sending people and so on disappear, right? So now what are you left with? Capital, equipment, plant? They already have it, right? They already have those locations close to every group of end users in the world where at least you have a wireline network. And on what else do you have? Energy costs, and you have bandwidth costs, the alternative costs of backhauling everything. And what we found out is for chatty applications, okay, and for applications that need low latency, think online gaming, think virtual desktops, etc., it is the optimal solution. For things like CRM or others, where you need a bunch of, or you know, medical research or wherever, what you need a lot of computational and you're not performance-centric, you just need cheap compute, it's the worst possible solution. And that's where optimization comes into play.
But the question is also where the storage is. It's not just the compute.
Yeah. But somebody
So,
said
so
it before.
say that again.
I mean, the problem in the cloud is not just the compute, it's also the storage and connecting all of the above. So you may be able to put a number of servers in the CO, but then if you want to put the storage and back it up, it's going to be very expensive. But we see different types. I mean, we believe that a cloud needs to have a very efficient infrastructure, compute and storage, not just compute. If you want to put in the central office also the storage, it starts to have a pretty big headache to put the storage and the compute in the end of the curve. So
that's where interesting things around distributed databases and so on come into play. But again, I don't think it's an either or.
I agree.
It's combinations, and you'll have multi-tiered applications that part of it reside at the edge and part of it reside in the core or in a central location. And the trick is how to optimize.
But the only person that can, the only business that can make money off that model is somebody that owns networks, because Google right now is not in the ISP business, and traffic costs 3,000 picocents per bit, whereas compute cycles are in the tens of picocents. So unless you can connect these edges very well, so I understand your business. I understand why you're pushing this, because you're in the business. You're in that business. Yeah. But for a current company that is not owning infrastructure, network infrastructure, they will have to pay you or whoever. I'm not sure if you guys are ISPs. I take that off. But they would have to pay Verizon or whomever for all that traffic to the edges, because and that may change their entire business model. Whereas today they have a bunch of these interconnected things where it could offer very cheap traffic inside and all kinds of cool things inside. And then as soon as you go from the East Coast to the West Coast, you're paying a lot of money. So so that's part of it.
Yeah,
Okay.
I want to ask you about what do you see for the future of cloud computing and its effect on the end user. For example, the telephone, when it was invented, there was needed a new networking system that eventually affected how people communicate. And now with the internet and the computer, and now the new inventions of the mobile device, what do you think might happen for a new interface between human and the computing world that the cloud computing might bring? Like
in the future, you'll just think, and the thing will do whatever you think. That's where it's going to get. Basically, someone will figure out your brain, you'll just have to think, I want those shoes, and they'll be there.
In Bell Labs, we're also working on something that entrepreneurs in the room would really like.
And by the way, if you want, you can join Mellanox. We're working on this.
Yeah, so along those lines, in Bell Labs, we're working on this is very good for entrepreneurs, by the way. PowerPoint to product compiler. Works very, very well.
By the way, you know, it's good sound. I think it's a great question, but this is where we're heading for, is that you will be very intuitive, and the machine will figure out exactly what you want. There'll be different stages. Initially, you'll maybe doing head moves or just speak to the computer, but eventually it'll figure out exactly what you want. It will learn the patterns that a lot of people think and want, and that's one of the big data problems, to make the right conclusions out of all the data that's out there, from videos, from pictures, from what people have done until now, from the health, the way that people walk and so on. The computer will tell you where to go, how to do, and a lot of things, because it knows so much thing because of all of the data that's out there.
So do you mean that the computer are becoming smarter and we are becoming dumber?
No, of course not. It's just that the computer learns your behavior and has much more data to tell you, I think that's what you want, and we'll offer that to you.
Which means that we become dumber.
No, we don't become dumber. Well, we just do the same things, but we get it faster. It's more efficient. I don't think we become dumber. I think we become smarter.
Okay.
About your question, I
you
think
can
that,
answer,
for
but-
example, part of the tablet revolution couldn't happen without cloud computing, because all these small devices that actually needs a backbone of fast computing or couldn't happen, some of the cellular phone application and the tablet and so on, without good cloud computing infrastructure. On the other hand, there is, to be serious about the dumber and smarter, there is a big threat for us. For a small example, there is a big debate about if it is allowed to use GPS to know what is your location. Practically speaking, if you have the biometry measures and you have all these street cameras and you have enough compute, you don't need GPS. All the camera can know exactly where you are, what you are doing, where you are working, without your permission or without any regulation. This is something that everybody can do. So there are a lot of issues that actually these smart devices can know about you and indirectly impact the way that you behave and how you expend your money, what you want to do, because they can, for example, send you specific ads that they will impact your decision what you want to buy or not, etc. So this is an entire issue of the relation between man-machine interface, which I think that we are not dealing enough about the psychology, about the sociology impact of this trend, but it happened.
Yeah, that's a different class. Yeah.
So I had a question that I don't know if it's for Scott or someone else on the panel, because I agree that the issue of reliability, and in particular in a large-scale system, is sort of very important. And if you think about the mainframe folks had that down to the last level of detail, but it was a very controlled environment where they understood all the pieces and they could migrate processes back and forth without really having to worry about things that they didn't control. The cloud is very different in the sense that especially if I look at a bunch of small distributed clouds or data centers and a network in the middle, right? So now you have many things that can fail, and so if you had one big, huge data center, you could probably always find something in there that can, replay or using some of the paradigm that Scott, introduced, sort of have this granularity where you can sort of fix the problem. But if it's now distributed across a network, what's the right option, right? I mean, sort of when things are all over the place, I mean, should you concentrate them at one place and then hope to have better recovery capabilities, but then it may not be optimal from some other sense, and how do you determine what's the right answer?
I mean, I think a lot of this depends on what you're doing. And for the kinds of things I tend to think about, which are sort of big data applications, typically all the data is sitting in a single data center, and you don't want to artificially spread it. You may have sort of duplicated the computation, but the transmitting the data over the network is such a big loss, and that the scale of your computation is such that you're running on a small fraction of the data center. You know, I'm running on 200 nodes out of 100,000. If I've got a problem, I'm going to be able to find another node. You know, if you're running some much larger, like you're doing the sort of full index for Google or something, all bets are off. I don't know how you scale that. I mean, and spread it across data centers. But for something that's a small fraction of the number of nodes in a data center, I don't see why you would spread the computation.
Depends on the application. If you look on maps, the probability that somebody from Israel will ask about the maps of Israel is much higher than the probability that somebody from cyber will ask about the maps of Israel. So it makes sense to distribute the knowledge and the algorithms to be close to the consumer.
But I was assuming that would be more like you would partition the map problem. I mean, you wouldn't, when I'm talking about distributing, you don't want to sort of distribute it in such a way you have a lot of communication going on.
It may happen from time to time that I will ask about some map in Alaska. So it is not that all the time the computation about the maps of Alaska will be done in Alaska. Most of the time it will be there, and sometimes I need to bring it closer to me. But the probability that somebody in Alaska will use it is higher. So in such application, it makes sense to try to distribute the data so it will be closer to the consumer.
I think the difference is, in that case, I would say you're replicating the data. I would not say, I'm going to that if you have a query from Israel that's asking about a map in Israel, I don't think that is going to be partially computed in Israel and partially computed in many other places. And so you either have a copy of the data local, or you go to, you know, the Uber copy somewhere else. So, I mean, I think that kind of sort of how you structure it so that where the data happens to be sitting, you absolutely distribute that way. You just don't want to sort of, during the middle of the computation, have to do a lot of communication because that's going to take a hit. So I think we agree.
Dor, I think it was you mentioning about the federation as a key challenge, right?
The what, excuse me?
Federation.
Yes.
You identified it as a key challenge. And I remember Eyal reminding us today the history of the internet and the importance of interconnection. We know why it worked in the internet, interconnection, right? But we know that federation didn't work, for example, in CDNs. CDNI, for example, at the ATF is 10 years old RFC. Nothing happened because of business reasons. Regarding the cloud, I think that the business will be completely different with and without the federation, and I am quite afraid that the same thing that we saw in CDNs will happen in the cloud. I would like to have your opinion on this. I mean, I fully agree that it will be a key driver for new business models, but I am afraid that it will never happen because two strong actors are already playing in the ground.
Yeah, so frankly, I think what's interesting about this space is it's driven by developers, and developers are doing what's best for them, right? And they don't want vendor lock-in. Along the lines of your previous question, will it be too expensive, et cetera? If it will be too expensive, they won't go there, right? The only way for this, I think, to work and really scale and really for the industry to adopt it is if there's mobility and there's no lock-in. And it's not that complicated at the end of the day because all of these different clouds have APIs to them, except they define things differently, right? A virtual machine or the size of a machine in Amazon is very different than the way that Rackspace defines a machine, and the interfaces are different, et cetera, et cetera. So the way to do it is for the open source community to deal with it, and in fact they do. We contribute a lot of code to an open source project called JClouds, for example. And in our first implementation today, for example, if you go to a service provider that implements our solution or someone else's type of a solution, you can use their own cloud, or you can use Amazon, or you can use an OpenStack implementation, and very soon you'll be able to use Terramark, so it's programmable, so it's solvable. It just needs to be dealt with, and the ecosystem needs to step up and do it, and you know, and I think it's, you know, it's funny because inside Alcatel Lucent, for example, people think we're crazy that we're contributing source code or that we're helping the customers actually not use the clouds we're building, right, and use someone else's cloud. But we think it's the only way it will work, because otherwise you might say, why would I go to Verizon's cloud and not to Amazon? But if I can leverage Verizon's cloud in what they're best in, and Amazon in what they're best in, and I can move around between them, then there's a shot for everybody in the industry that can add value to allow people to leverage that value. I think the question was, do you need standards to do it? I don't think in this environment you need standards. What you need is action by developers. So what's interesting, I think, in this field, and definitely strange for a company like Alcatel-Lucent, is it's not being solved in the IETF or TMF or IEEE or IETF or one of those things, right? OpenStack is a good example. OpenStack, you can argue as much as you want about the implementation of OpenStack, but what it really is strong in is a standard API to how to work with an OpenStack cloud, and then you'll have different implementations of OpenStack underneath. And I think that's going to continue to happen. We just saw Citrix open source Cloud Stack, and they're opening their APIs there, and I'm sure those things will talk to each other. And JClouds is running well, and all of those things. So I think it's not going to happen by a standard. It's going to happen by people contributing code and developers adopting it and adding to it, and that will become the de facto standard. But I'm interested in what other people.
So my question is, if I have an application and it's running now in my data center on my resources, and I want to apply it to the cloud, to deploy it on the cloud, how do I know which resources or what resources do I need to rent in the cloud? I mean, should I rent, is there a precise way to estimate the application's needs? I mean, in terms of CPU and RAM and all the resources it might consume?
Yes.
It's
mostly an art, obviously, but what you could do is you could profile the application. You can hire someone to do this for you, but you could profile your app, and you can decide why you want to go to the cloud and how much you're willing to pay for it, because you may pay more in the cloud, but you may get all kinds of other cool things in the cloud. And then the profile will also tell you how much you're going to actually pay. And there's some profiles we have built, and again, this is not what my company is about. This was just fun stuff we did over the summer. That were very accurate. They were pretty accurate for pretty complex applications. So if you're just talking about, if you're not worrying about the cloud managing stuff for you and licenses and stuff like that. And again, I'm not referring too loose to cloud here. Everybody talks about cloud as if anything that's connected to an IP address is cloud. I'm not talking about that. I'm talking about using Amazon and outsourcing your stuff to Amazon, and possibly with a little bit of layer of some sort of infrastructure in there. So you could profile your networking needs, you could profile your storage needs, you could profile all these things. You can actually profile them, literally profile them, apply profilers to your app if you're serious about it. So Merrill Lynch does this, for example. They're trying to see if...
But there is no automatic way to do it. There is no way to automate this. I mean, you can do it manually. You can do it for each application manually, but you
there are companies that sell stuff where you can profile. You can outsource stuff to the cloud, and then it will profile stuff for you as it runs, and
so
they can tell you how much.
They deploy it and then they test it. I mean, they
no, they're not going to take your app, and I mean, there's many millions of companies, but the ones I'm talking about are companies where once you outsource, they will start counting the beans for you and telling you which part is not worth outsourcing and so on. And there's layers for Amazon for rack space. There's layers for the CA cloud. So there's a lot of these, but I don't think you need this. I think you need a consultant that will profile your app manually, and he'll pay a lot of money for that, unfortunately.
How do they? I mean,
no, I'm not selling at all. I don't sell this thing.
That was the last question.
I'm not selling the services.
Okay.
What about if they want to scale? If my application now needs to scale up or scale down? I mean, how will they profile
it's
my
It's a trial and error. You
resource
just need
consumption?
to try, and whatever it works, it's great. If it doesn't work, you need to scale up or down.
What's the price you're willing to? What's your price you're willing to pay for scaling up? That's another question. Because right now it may not be worth to go to the cloud, but you pay that price for being able to scale later on.
One comment that, at least my experience, is that if you have the application and you know how it works and so on, so all the calculations are perfect, etc. But usually when you're at a development stage or at early stage that you don't know what the traffic will be and so on, it is much better to go to the cloud because of the flexibility and because of the opportunity to check different trade-offs and so on. And only after you understand how your system will work as a production, then you need to optimize and find the best way where to run it, etc.
Okay, that's it. Our time is up because somebody else is coming to the here. Thanks very much.